And I say, let's get started here. All right, again, thanks everyone for joining to this October session on the Data Science and AWS Meetup. Thanks for joining us today. We do have a packed agenda. I'm super happy to introduce our speakers here in a little bit. Just a quick intro. Some of you might be familiar. Chris Fregly and I were running this meetup, monthly meetup, Data Science on AWS. We also co-authored a book together. So if you're interested in learning how to do data science on AWS, how to build end-to-end pipelines, how to really do all of the steps from developing machine learning models, from ingesting data, analyzing the data, to preparing features, training, tuning the models on AWS, and also a lot of more content, check out this book. It's on Amazon, and Amazon actually does have a special this month. So there's a 54% discount right now. So if you haven't done so, check it out. It's a great discount offer currently on Amazon as well. And also, we're running those meetups here monthly, where we're always inviting guest speakers to present, same as today. So please, if you go to datascienceonaws.com, I'll put the link here also in the chat. There's a lot of information. Here's links to the book. We have done some workshops. We are running monthly meetups, and also here a link to our GitHub repo, which contains all of the code samples that we built to write the book. So there's a lot of good content there. Check it out. And also there's a link to the YouTube channel. So we do record today's session, and we've recorded previous meetups and workshops. So if you want to have a look at those, also you can follow the link here that points you to the YouTube channel. And with that, let's have a look at today's agenda. Let me zoom in here. I'm super happy to welcome our first speakers, Aaron Sengstacken and Heiko Hotz. They're working both as ML specialist solution architects at AWS, and they're going to present on how to leverage HuggingFace on Sagemaker to create NLP models for contract review. And we also do have another speaker today. So I'm also super happy to introduce briefly Shayan Kumar Saha. He's also working as an ML solution specialist, solution architect at AWS, and he's going to talk about computer vision models. So I think we haven't had a guest speaker or a session in a long time focusing on computer vision. So I'm super excited personally as well for this talk. Shayan will introduce us to the NVIDIA DALI library and show you how you can leverage together with Sagemaker debugger. So really, really cool talks today. And with that, I'm handing it over to Aaron and Heiko for the first talk today.
Perfect. Thanks, Antje. I'm going to try to share my screen. Just give me a second. Okay. Just let me know if you can all see my screen.
Yep,
yes, we can see the slides. And just a quick note to the attendees, if you have any questions for our presenters, please put in the questions in the chat or the Q&A, and we'll get to those. All right.
Perfect. All right. So thanks everyone for joining. Today, Aaron and I are going to talk about how to leverage NLP models to help with contract reviews. So we're going to have a quick look first at what are contract reviews, and then how to train and host and deploy an NLP model that then helps you reviewing those contracts in an automated fashion. Before we go into that, just a few words about NLP at AWS. There's many different ways how you can do NLP at AWS. We have quite a few AI services. You might have heard of some of those: Amazon Comprehend, Amazon Transcribe, Translate, and so on. We also announced earlier this year the HuggingFace partnership. So that is a partnership between HuggingFace and AWS that allows you to leverage the models from HuggingFace directly in AWS. And that is something that Aaron and I have done in this particular case. And we love to show you more about that. And there's also many more possibilities on how to do NLP at AWS. And one of the challenge that we saw is giving like all these tools like AI services, HuggingFace, all the other possibilities. There's no like one right answer. Each customer is a bit different. Some customers might benefit from the AI services, others from machine learning models where they can customize a bit more. So in order to guide the customers in their NLP journey, we have created the NLP domain within AWS. And what the domain really does is try to enable the field, and that is our solution architects or business development people or account teams, to have conversations with the customers about NLP. And to that end, we publish externally, like publicly available NLP newsletter. We write blog posts. We do enablement sessions, very similar to this one. We provide code samples. And like one result or one outcome of the efforts within that NLP domain is actually the contract review demo that Aaron and I have built. So we are really excited to show you that today. And first, let's have a look what are actually contract reviews. So you can think of a contract review like a process of thoroughly reading through a contract and then to understand the rights and obligations of each individual or the company who signs the contract, and to assess the associated impact. That's a mouthful of words, but basically what you want to do is you want to extract key information from these contracts. These contracts are sometimes really long, and the pain points are that it is very time consuming for lawyers to go through these contracts. There's some estimates out there that lawyers spend approximately 50% of their time reviewing contracts. It's also quite expensive because you need specialized training to understand and interpret these contracts. And the billing rates for lawyers, at least in the US, are in the large law firms are typically around $500 to $900 per hour. And the consequences obviously can be dire. So small companies and individuals sometimes don't even, because they don't have the time or the money, don't even read through these contracts. And that then can result in predatory behavior and harm consumers. Now, obviously, contracts play a big role in the legal sector, but it's true for any sector really that deals with contracts. So that could be large enterprises, the public sector, real estate, and so forth. So how can NLP then help with these contract reviews? Well, ideally, what we would want is a machine learning model, an NLP model, that automatically reads through the whole contract and gives me the key information that I, as a lawyer, am looking for. And the idea here is not to obviously replace lawyers, but you can think of such a model as a tool for lawyers. Similarly, like, calculators haven't replaced accountants. We're not looking to replace lawyers, but basically give them a tool that helps them get these contract reviews done more quickly and with fewer errors. Now, what these NLP models usually need is they require annotated, labeled training data. What that is basically examples from the past where a lawyer has gone through contracts and basically annotated these contracts and said, like, this is the section where the governing law of the contract is described. This is the section where the agreement date can be found, and so on. And the idea is to take lots and lots of these examples and feed it into a machine learning model so that it can learn these patterns. So that it, and not only learn in terms of like, oh, I have to look for certain keywords. These NLP models, as we will see, are more sophisticated. They are able to understand the meaning of a sentence in a certain sense. So they are not, these contracts don't have to be written in a certain, like with certain keywords in mind. The models should be able to understand the meaning of the sentence and pull out the governing law, no matter how it is worded in the contract. Earlier this year, now, luckily, we have gotten exactly such a data set, the Contract Understanding Atticus dataset. It was created by the Atticus project, and it's open source, so anyone can download it. And what they did is they took more than 500 contracts, and they identified 41 key questions, like 41, you can think of like 41 key data points they always would like to extract from a contract: agreement date, governing law, are there any limits in terms of like repayments, and so on. They did more than 13,000 annotations. Overall, they annotated over 9,000 pages. And if you take the you know, the rate that we talked about earlier, between 500 and 900 US dollars per hour, you could estimate that commercial value of this data set to about 2 million US dollars. Now, the way, now that we have the data set, now we need to find a model that we can feed that data set into. And that's where question and answering models come into the picture. Question and answering models have had a renaissance ever since the famous BERT models came out and the famous transformer models. They have gotten better and better. And what they do is really a reading comprehension exercise where you give them a short statement or text, and you ask the model certain questions. This is quite a famous, the Squad Explorer, which I put here in the link, is quite a famous website where you can play around with these question and answering models. And you can see that some of these models, at least as of June the 4th, 2021, they outperformed humans in some of the reading comprehension tasks. Now, the way that you can think about how we're going to go about teaching the Q&A model, a generic Q&A model that we can download from a place like HuggingFace, to teach it to learn about contracts is via transfer learning. And transfer learning, the principle is that in traditional machine learning approaches, you can see them on the left, is you have a task, you have some data, and you train a model, and then you have a model for that very task. And then you have a second task, which is different from the first task, might be related, but still different. You train a new model from scratch for this new task. And for every task that comes after that, you follow the same approach. Now, the really key factor in how these new NLP models became so powerful and successful is that they use transfer learning. And I took this picture from a paper from 2009. So transfer learning is nothing new. Came up, I believe, in the era of computer vision. But basically what you do is, instead of training a new machine learning model for every task that you encounter, you take a few source tasks and build up a knowledge system And then when you have a target task, the task that you actually want to do, you just fine tune this knowledge system onto your target task. So what does that mean actually in reality? What you can, in NLP, what it means is you can basically teach a machine learning model and NLP model just about the English language, say. I feed it tons and tons of data, like all the Wikipedia articles that are out there and other text data in the English language in a self-supervised approach. So that means the model just studies all these texts, the English text that you give it, and it learns like what words go together with other words and what do these words mean out of the context by certain techniques. And once you have this English language model and you have now a target task, say sentiment classification, is it positive or negative text, or question answering in the legal contract domain, you can just take the data set that we have here in the QUAD data set, apply it to an already existing model, just fine tune it, and that will save you days, weeks, months of training, because these kind of fine tuning tasks can usually be done in the matter of hours. And to show you how you can download these models from a place like HuggingFace and train and deploy these NLP models on AWS, I will hand it over to Aaron, who will talk you through that process as well as the demo.
Awesome, thanks. Just to recap, like we're using a pre-trained model here that we're going to use transfer learning in the legal domain. We could do that with other domains as well, right? We could do that with the aviation domain. We could do that with manufacturing, anything where it's not conversational language that it's been trained on. And in many ways, humans do this already, right? I have a 6-year-old and I can teach him to play soccer, but I don't have to teach him to walk first. He's already learned how to walk, and we're just transfer learning to learn to play soccer, right? We do this all the time if we learn a new subject where we've learned to speak English or speak a language. And when we learn that domain, we're using transfer learning to pick up the new task. So let's talk about how we went about building this, this example. So I'm going to start with step 1 here, right? With a machine learning task, we have to start with data. And you could get data from a number of different sources. Here we use the GitHub repository of that quad data set. You could also use a HuggingFace data sets. You could use UCI repository. You could use a Kaggle data set. Many different places right now. And it's actually an interesting time that we live in because data is so readily available. But we have to download that data set. And when we say download, we really need to use AWS, we needed to get it stored in the cloud. We need to get it stored in S3 primarily. And S3 is a storage location. So if you're new to AWS, think of S3 as where I'm going to store my data. Might also have to process that data as well. Certainly in the real world, our data sets are not clean and they are not ready for machine learning, right? So there's a lot of processing, cleaning, munging of data. It's not just cleaning of data, but it might also be some feature engineering where we're converting a categorical variable into a one-hot encoded variable, or we're cleaning date timestamps, et cetera. We might be splitting that data set also into our training, testing, and validation data sets, or doing some type of cross-fold validation technique for our data set preparation. But once we're done with step 1, this is really the preparation phase. We're going to have a clean and stored data set in S3. And when we move on to the step 2 and start thinking about how do we want to train this model, it's really no different if we're using AWS or if we're using a laptop or we're using a server that's located in our office. We need some code to be able to train a machine learning model. And this training code is really the numerical optimization that's going to be adjusting the weights of the model based on the training data set. Right? So we need to write some training scripts. We have a lot of training script examples that are available for you to start with, and I'd recommend that you start with something than starting from scratch. So in this example, we're going to be using HuggingFace for our training. And when we kick the training off, we're going to, you notice out of the S3 storage in the middle, this is a bidirectional interaction with our training. Step 3 is our training step when we actually execute the training. It's bidirectional. We're going to be pulling data from S3. This is that training and validation data. We're going to be loading a pre-trained model from HuggingFace in this example. And this is based off of the Roberta Q&A architecture, if you're familiar with that. But there's a number of different Q&A architectures. And we're also going to be using a deep learning container that's going to encapsulate our training script. Right? So we have deep learning containers that are supported for HuggingFace, they're supported for PyTorch, supported for TensorFlow, and a number of different major frameworks. But we use that deep learning container to be able to run our training script on this EC2 compute instance. Right? This is where we're going to be able to use the power of AWS. And if you're familiar with SageMaker, or you've heard the term SageMaker, this is what's referred to as a training job. But again, as Heiko mentioned from the beginning, there's many different options with AWS. You could do this standalone with EC2 instances. You could also do this with SageMaker training jobs. You could do this with SageMaker Studio. But the end of step 3 is now we've taken that pre-trained model from HuggingFace. We've trained it on our data set that lives in S3 using transfer learning. Now we have a model that can understand legal contract text. And we save that model to S3 as the output of number 3. But the last thing we want to do is we want to deploy the model. We want to use it. Right? We want others to be able to use it. So we have a number of options of deployment on AWS. We could deploy to an EC2 instance, and we could do that manually, or we could use SageMaker deployment. And these could be real-time deployments or batch deployments. There's a number of different options. We could also deploy our model to a serverless function, or also use a container and a container service like Fargate to deploy our model. We could also download our trained model and use it ourselves. Once we train the model on AWS, that is our model artifact to use however we please. Right? We could download that and deploy it to an embedding device. So lots of flexibility on the deployment side. Let's go to the next slide and talk a little bit about the architecture that we used in the demo that we're going to show. Okay, so on the right-hand side, the SageMaker notebook and the container registry and S3, that's what we talked about, where the end of that training was a SageMaker real-time endpoint. This is a live 24 hours a day, 7 days a week, real-time endpoint with a GPU that's supporting that endpoint. We then developed an app to interact with that endpoint. And here we're using a Streamlit app, so it's Python-based. There's a number of different options to build quick user interfaces. We use Streamlit, but there's other available. We containerized that code and then deployed it to ECS, so container service, and deployed it to 2 different Fargate instances. We put it behind a load balancer, and we authenticate our users with Amazon Cognito. This basically just allows us to authenticate who can interact with the app. And then we put it behind a custom domain name as well. So the end users are interacting with that Streamlit application, and in the back end, we're interacting with the trained SageMaker endpoint. Let me show you the actual demo now. So maybe I'll switch screens here, take over. All right, let me make this just a little bit bigger. Okay, so this is a Streamlit app that we built. Again, this is contract legal understanding. So when you come to this app for the first time, you have options of what contract do you want to select. And we can either use a surprise me function here, where it's just going to pull a random contract from that data set that we discussed earlier. And it's pulling it from the test data set. We want to make sure that we pull from the test data set because we don't want to use something that the model was trained on. So we can do a surprise me. We also have 3 contracts that are preloaded, and we'll look at those in just a moment. You have the option to upload your own contract, and we support Microsoft Doc, X, PDFs, or text. just raw text if you want to upload the raw text. So let's show you a couple options here. I'm going to use a third contract, these three contracts that are pre-built. And this is a contract, again, from the test data set. This happens to be a co-branding agreement between Arnold Schwarzenegger and 2 other fitness companies. But we can start to ask questions of this contract. And we'll start with something quite simple here if we want to look at the questions. Again, the quad data set has 41 questions that we can ask. Here, let's ask, which state or country's law govern the interpretation of this contract? And this is one that I could probably answer. I'm not a lawyer, but I could probably answer this by reading it. Let's see if the machine learning model can answer it. We can see the answer here is below. When we click analyze, that we get the agreement has been executed and delivered in Los Angeles County in the state of California, and all laws of the state of California. Okay, makes sense, checks out. But there are some questions that as a non-attorney, I would have a very hard time answering, even if I read the contract. And we can take a look at, let's look at another question here. We can look at revenue or profit sharing. We could also look at what are the terms related to the license grant. This is a co-licensing agreement. So let's look at question 26. We'll analyze it for question 26. And when we click analyze, we're interacting with that real-time endpoint that we deployed through Sagemaker. And we get an answer back, right? This is text from the contract that it's saying they have right to use the trademarks as defined in the agreement, name and appearance rights, video, recordings, number of things around what is the grant of the license. Right, pretty cool. We also built some options into this demo because machine learning models aren't exact all of the time, and there's not always one best answer. Many times there's a couple of great answers. So you can adjust the number of results to show here in the left-hand side. So let's change this to look for 3 different answers. So now we'll get 3 answers back. We'll get the top 3 answers. And we can also show the probabilities. So what is the confidence associated with those answers? Here we'll take a look at another contract. Contract 1 happens to be between the National Football League Alumni Association. And this is an endorsement agreement. So real quick, we can take a look at, let's take a look at question 36. What is a text that describes the cap on liability upon the breach of a party's obligation? Again, this would be fairly difficult for me to answer without having that legal domain, but let's see how the model performs. And now, because we've selected the options for 3 different results, we can see that we have 3 different results in the text window and their associated probability. Right? So the 3 results, we can see that the top result had a 51.9% probability. We can see that the agreement for cap on liability incurs expense, damages, and other liabilities, but doesn't exceed the remuneration and excludes the reimbursement of expenses. If you look at result 2, you'll actually see it's the same text, but just expanded a little bit. Right, so this is the same. The second result, the second best result, is that same text, but expanded out just a little bit. And this has a confidence score of 32.6%. With a question answer model, though, it's actually acceptable to have no answer. And let's take a look at that. What sections relate to irrevocable perpetual license? No answer is found. We want that to happen, right? In a QA model, we want to be able to have no answer found. And some of these contracts, they aren't going to have licensee and other required termination clauses. They might not have other IP clauses, and we want to be able to have no answer found. So in QA models, that's perfectly acceptable. We'll look at one more here. Question 6 is, what is the renewal term after the initial term expires? And again, the model is going to interact with that Sagemaker real-time endpoint that was transfer learned with the HuggingFace model. And here, the renewal term after the initial term expires talks about it gives a long product development lead time. and they're going to begin discussions for the renewal no later by June 1st, 2020. And so this doesn't tell us what the renewal term was, but it tells us when it's going to start. Right? So this was still the best answer at 93% because there wasn't a renewal term in this contract. All right, so very powerful to take a domain-specific task that's expensive, has high consequence, to really empower legal teams to be able to use a model like this for efficiency. Right? This is, again, not intended to replace the legal team, but augment it and improve the efficiency. So with that, we want to open it up to questions. We'll share a few links for the blog post around this data set, the Squad Explorer, and the paper associated. But I want to thank you for your time and open it up for questions.
Yes, thanks so much, Heiko and Aaron. Great session. We got a ton of questions here in the chat. Just really quick, make sure you're flipping when you're answering to send to everyone. So the host and panel, otherwise the attendees wouldn't see. So yeah, maybe you can spare a couple of minutes here and go through the questions. I think, Aaron, you started answering before you took over the presentation, and Heiko is doing a job here in answering. A lot of questions, I think, around where the questions are coming from here in the data set. Can you share any resources, a GitHub link, or I think you have blog posts, right, that discuss the setup as well?
Yeah.
So please, yeah.
The paper that you also shared, Antje, the archive.org paper, I shared it again. That is basically all the work that the team did that developed the data set and the questions. So much more information can be found in that. It's a non-technical paper, so it's a really good read, actually.
And that paper used 41 questions, but there's no requirement to just use those 41, right? If you had another task that maybe you wanted to train a model on 50 other questions that you were adjacently interested in, you could do that as well.
Perfect. Yeah, there's just one coming in. Can you briefly talk about the model architecture of the fine-tuning part?
Yeah, I mean, that's what we try to show in the one slide with all the arrows. But basically, what you do is you download a pre-trained model from a place like HuggingFace. You store your data set in S3, and then you spin up an EC2 instance where you download a container image that has all the requirements installed, and that's where the training basically happens. It's with Amazon SageMaker, and I saw there was a question about what is SageMaker. So Amazon SageMaker is AWS's machine learning platform. With SageMaker, it's super easy. It's basically a one-click training because you just push one command, and then all this stuff of like spinning up an EC2 instance, downloading the container image, pulling the data, all that happens with one command in SageMaker.
And this was based off of a transformer-based architecture, the Roberta architecture that was used to fine-tune it.
Great. Yeah, I think there's a lot of questions, so I'm just conscious also about the timing of today. So yeah. Aaron, Heiko, if you could spend a couple more minutes and go through the chat window, share the links you have, and see if there's any questions still left unanswered, and we'll get to all of those. So if you have any remaining questions for Aaron and Heiko, feel free to put them in the chat. And yeah, I'll say thank you so much for the session. Maybe we need a follow-up. There's huge interest in this topic, apparently. And it's a great use case also to see how you can apply NLP and work with transformer models. All right, so with that, I'll actually hand it over to Cheyenne, and we'll switch over to computer vision. I think you have to unmute, Cheyenne.
Yeah.
Yeah.
Thanks, Antje.
Now we can hear you. Perfect.
Yep. Let me share my screen. Yep. You can see my presentation screen, right?
Yes, we can see it. Take it away.
So, one moment. Yeah. Hello, everyone. I'm Shaun. I'm a machine learning specialist solutions architect based in Berlin, in Germany. And I work with AWS customers, helping them to scale their machine learning solutions using the AWS infrastructure, focusing a bit more on the computer vision domain. And yeah, thanks earlier to the great talk with NLP and the contract demo that we saw earlier. We already saw a little bit of Sagemaker. In this talk, what we would see is basically we will address one of the common problems that we face when we do computer vision training, which is the data pre-processing or the image pre-processing bottleneck in the CPU. So what we're going to do is the topics we're going to talk today is I'll start with a very brief overview of what is Sagemaker. I think that will be useful given there were some questions I noticed on the chat earlier. And then we talk about what happens specifically with this bottleneck. What are the problems? What are the challenges out there with CPU bottlenecks in computer vision use cases? And we will look into the experiment we conducted to address this problem. And we will see how we can use Sagemaker debugger to identify these bottlenecks. And we will zoom into one particular training job and see for certain models, how much can we improve by addressing this data pre-processing bottleneck in the experiments. Before we start, what exactly is Amazon Sagemaker? So as already discussed briefly earlier, this is an end-to-end service for machine learning from AWS. It is a managed service. That means data scientists or ML practitioners can get rid of the undifferentiated heavy lifting that's associated with machine learning, so that you have more time to focus on your business problem at hand and not care about the infrastructure, right? And Sagemaker provides users with an integrated workbench, like one single glass pane called Sagemaker Studio. And if you know Jupyter Notebooks, you can launch Jupyter Notebooks and Jupyter Lab environments instantly through Sagemaker. And also with this entire managed infrastructure approach, you can go beyond notebooks and also have different experimental setups, setting up distributed training clusters, hosting. We will see Sagemaker debugger, how it can help you identify bottlenecks, have some visualizations, and you can do all of this while Sagemaker takes care of scaling, patching, high availability, etc. that's associated with the ML lifecycle, right? And as I mentioned, that Sagemaker has different features across all the different ML lifecycles. So starting from the preparation phase to model building phase, and then training and tuning phase, and finally deploying and management phase. So all of these, Sagemaker has different features for all of these stages. For this use case, we focus on a Sagemaker training example. And as Heiko already mentioned in the previous section a little bit, what happens in Sagemaker training is basically every time you want to run a model, Sagemaker has its own ephemeral cluster that spins out, and you only need to provide which S3 bucket has your data and some piece of code from the Sagemaker SDK. And with that, Sagemaker can spin out a dedicated EC2 instance that you would mention, which will be alive only for the time when your model needs to be trained. And once your model is trained, this cluster would be automatically taken down after the process finishes. So that way you have, that's the way you can run remote training jobs on Sagemaker and focus on the algorithm or the model and not take care of managing the infrastructure or managing the EC2 instances with the GPU. Yeah, and for this particular session, we talk about computer vision training. And before talking about the bottleneck, what happens typically in a computer vision training scenario is you have the data in a storage, in this case, for example, in an S3 bucket, and you have batch of input training data that is being fetched from here onto the CPUs of the training instance that you are using on Amazon Sagemaker. And then typically you would do some pre-processing and data augmentations. So image decoding and image decoding followed by other use case specific augmentations. And then the data is there on the GPU. And on the GPU, you would have the forward and the backward passes for the input batches, where the GPUs periodically can pass model weights, loss, matrices, and other information to the CPUs. And finally, on the CPU, you could have potentially some post-processing, but basically you would be probably generating some checkpoints or finally finish the training the model, and the model would be stored back in the S3 bucket. In CV use case, what we potentially see is a bottleneck where the data being pre-processed, this causes the CPUs to be overwhelmed, which actually leads to GPUs starving for the data. So often there is a requirement for heavy image augmentation in image classification, segmentation, pose estimation, or other use cases. And data pre-processing when dealing with JPEG images typically consists of two steps, if we zoom in a little bit more. First step is decoding of these JPEG images. And the second step is the use case specific augmentation. Now, we know that a single GPU can perform terafloating point operations per second, which allows them to perform operations very fast compared to CPUs. But for GPUs, which is an expensive resource, to perform such operations, the data must be available on the GPU memory as quickly as possible. So the challenge lies in the fact how to optimize this flow of training data such that GPU is never waiting for these computations, and basically you are able to maximize your usage. And in a nutshell, this bottleneck occurs when basically the ratio between the data pre-processing load that you have on your CPU and the model computation load that you have on your GPU, when this exceeds the CPU-GPU ratio, this is when this bottleneck occurs. And this is the challenge that we are talking about. And although on AWS, you can see we offer an array of instances with different CPU and GPU ratios, there's not one silver bullet to find that optimal balance, and this between the number of CPU and the number of GPUs. And also the requirement keeps changing depending on the size of the data, the increasing augmentation load, or even the model complexities. We have quite a few customers, especially in the CV space, who face this challenge and take up different approaches to address these. One of them is, for example, for the document verification use case, where the customer has pretty large data sets of JPEG images. And apart from the different IO challenges or the network challenges that they would overcome, one issue is the bottleneck caused in training between either underutilization of CPU or underutilization of GPU. So when they use smaller models, they spend a lot of time on the CPUs for decoding the images, and this is causing the GPUs to be idle. And once the model becomes larger, the GPU starts to become the bottleneck. So there is a lot of experimentation involved to hit this right chord for maximizing the performance. So what we do in this experiment is we try to reduce the training time by addressing this bottleneck and we do this by moving this JPEG image decoding and augmentation on the available GPU instances on Sagemaker. So, and the way we evaluate in this experiment is we measure it by seconds per epoch. As I mentioned that Sagemaker has ephemeral clusters, and you only pay for the time in which your training your remote training job is being run. So in this case, if we can improve the seconds per epoch for model training by visualizing the system utilization, this also reduces the cost proportionally. And that's a great benefit we get when we can improve our resource utilization. So yeah, some details about the data pre-processing experiment itself. So we here use the ImageNet dataset, which has an average image size of 144 KB and a total dataset size of 1.3 GB. And we performed this experiment with 3 different models: ResNet 18, ResNet 50, and ResNet 152. And we specifically choose models of different complexities so that we can better visualize how we are addressing the bottleneck. And we use the MLP3 2x large instance, which has 8 CPUs and 1 GPU. We can definitely use larger instances, but in this experiment, the idea is to show how we can improve the resource utilization for a given GPU, for a given instance, even if it's a smaller instance, without simply vertically scaling up, right? And as already mentioned, Sagemaker provides various containers. And in this case, we use the PyTorch estimator. So we are using a PyTorch container from Sagemaker. And to do this training, we use a batch size of 32 epochs. We run 2 epochs with 298 steps in each epoch, and we see how it looks like. So what are the augmentation operations we do to measure this bottleneck? Let me just check. Yeah, so we start with decoding. So that's the first step. And once we have the decoding, what we do is we do a horizontal flip, vertical flip, and random rotation. So of course, in real world, there could be various other augmentation operations involved. But in this case, what we do is we do these 3 basic operations, and we increase it by a load factor for the sake of experimentation. So that we can mimic how it would actually look like when in real world you would have more heavy augmentations like Gaussian blur or dilation or jitter or other heavy augmentations that you would pick up. And once we repeat these augmentations multiple times, we resize the image, normalize it, and crop it. And that's the flow we continue when we are actually doing the entire training process for every run. And for this data preprocessing experiment, basically we take up 2 approaches. So in the first approach, we use the native pipeline of using PyTorch data loader for augmentation as a baseline, and benchmarking and identifying the CPU bottlenecks. And in the second approach, what we do is we use the NVIDIA data loading library known as NVIDIA DALI. And we use this DALI library to configure parts of the data preprocessing pipeline to run on the GPU. So just a bit of background, DALI relies on its own execution engine. So it is built actually to maximize the throughput when it comes to such input pipelines running on NVIDIA GPUs, which is the case in our scenario. And features such as prefetching, parallel execution, batch processing, these are handled by NVIDIA DALI itself pretty transparently. Another important thing to note is DALI also comes with the NVJPEG library, which is actually used for GPU accelerated JPEG decoding, unlike in the PyTorch data loader where we do this decoding on the CPU, right? So we run this experiment for all the 3 models using these 2 approaches. And then we check how does our experiment results look like for that scenario. Yeah, so now we are looking at ResNet model training time for augmentation on CPU versus when we offload it actually on GPU. So on the y-axis, we have the seconds per epoch. And on the x-axis, we have the increasing load. So 1x means we do the flipping operations that we showed earlier. We do that one time. And with 4x, we increase it 4 folds, and then 8x, and then 12x. And then we increase the augmentation load. And then we see how we are reaching some bottleneck and how they are being addressed. So what we see is with PyTorch, when we use PyTorch data loader with the augmentation on CPU, this is how the training time looks like for different augmentation loads for ResNet 18, which is a comparatively smaller model compared to ResNet 50 and ResNet 152. And once we manage to move this decoding or augmentation operation on GPU using NVIDIA DALI, we see that we have managed to improve the training time quite a bit. We repeat the same experiment with ResNet 50 model. And then we see that for ResNet 50 model, how the improvement in training time occurs when moving the augmentations to GPU. And we repeat the same experiment for ResNet 152, which is a heavier model. So of course, you can see as the model gets heavier, more compute intensive, the training time overall increases. But you can see that with the second approach, the training time reduces drastically. Now, what would be the other correlation, if we think of it, between the improvement time between these three different models? So here you can see this is a chart where the x-axis and the y-axis is the same. The augmentation load factor, increasing augmentation load factor, and the improvement in training time. What changes basically here is we plot the improvement time. So you can see that for ResNet 18, the improvement with increasing load is much more than ResNet 152. So that really tells us that lighter models like ResNet 18 actually cause more CPU bottleneck with the same augmentation load. And when using such approaches, as I mentioned earlier, there is no one single silver bullet to improve the training time in such scenarios. It always depends on what data you have, what augmentation you have, what model are you using. Keeping the other variables constant, we see quite a steep improvement in ResNet 18 compared to ResNet 152. So that's one part of the experiment. Next, what I would like to show you is how do we actually visualize these bottlenecks when we are using Amazon SageMaker. So when it comes to bottleneck visualizations, this is basically what I mentioned right now, that lighter models cause the better training time improvement. But moving on to the next topic is SageMaker Debugger. And this is a feature of SageMaker training that makes it easy to train ML models faster by capturing real-time metrics. So for this use case, we don't focus on the model-specific parameters such as loss or learning gradient or weights. These are things that can also be captured by SageMaker Debugger. But in this experiment, what we discuss about are the framework matrices and the system resources, the monitoring abilities to identify the resource bottleneck. So that means how long did it take for every step? How was the data loading time? How was the pre-processing time? Where exactly are bottlenecks being caused? Is it the IO bottleneck, or is it the GPU starving for CPU bottleneck? So in this experiment, we focus on this part. And you can use SageMaker Debugger both from the SageMaker Debugger library that is being provided, SM-Debug library, and also from SageMaker Studio, the IDE that I mentioned earlier. You can also visualize it directly from the studio itself. So let's see what insights do we gain from SageMaker Debugger for this particular experiment. So just going ahead. Yeah, so if you remember this chart, what we do is we zoom into one particular experiment, which is this experiment where we have a 12x augmentation load, and we are using the ResNet 18 model, and we see how much exactly have we improved and how did the bottlenecks look like in both the approaches with the SageMaker Debugger. So this is with the first approach, where we are using PyTorch data loader. And this is a screenshot from the debugger profiler that can be, as I mentioned, either accessed from SageMaker Studio or S3 bucket. And this table basically shows the usage statistics. So how, for one worker node, right? So how the CPU and the GPU utilization percentage looks like for minimum, maximum, and different percentile values. So in this case, you can see that the P95 value for the CPU is 100, which means it's pretty overutilized. But the GPU utilization is only 31%. And what I do is I use the SMDebug library, which I mentioned earlier, to generate the following heat map, which actually provides a visual representation over time on how it looks like. So in this case, you can see that I have zoomed into the bottleneck area. And on the x-axis is basically the time, and y-axis is you have the different CPUs and GPUs. So this is an example where I have 8 different CPUs and 1 GPU. And you can see that GPUs have frequently stalled cycles where GPU utilization drops to 0. So that's the purple part. And you can see a lot of yellow in this chart, which means that there's a lot of, due to the augmentation load, a lot of CPU is being overutilized and almost reaching 100%. Now, we do the same thing by moving the decoding and the augmentation to the GPU using NVIDIA DALI. And there we see that in the previous case, we had 77 seconds per epoch. And in this case, the seconds per epoch with everything same, just moving the decoding and augmentation on GPU, we managed to drop it to 21 seconds. So that's an improvement of over 72%. And if we look into the same profiling report from debugger, we see that the GPU percentage has increased to 55 from it was 31 before, but the CPU utilization has dropped from 100 to 64. So that means it's a better load balancing at this point. And you can see the GPU is only at 55. So even if we would increase the augmentation load from 12x to probably 16x or 18x, it can still handle that load and still keep the seconds per epoch pretty low. And there's the interesting part where we also see that we clearly see the improvement that has been brought around, where we see that the CPU utilizations have improved. They are not overloaded like it was previously. And the GPU utilization, the GPU is being much more utilized much more efficiently when we take this approach. Yeah, that's more or less what I wanted to showcase. So this is a repository. I can share it in the chat after a while, which has the implementation of using NVIDIA DALI with Amazon SageMaker training. And as I mentioned, I mean, deep learning applications, specifically with CV use cases, often require complex multi-stage data processing pipelines that can include loading, decoding, cropping, resizing, and other use case specific augmentations. And just to summarize, we often see that these pipelines, which are natively executed on CPU, often become a bottleneck. There are several approaches, and one approach is to be able to offload some of this load to the GPU and to load balance it better, depending on what model you are using, what data set you are using, or what kind of loads you are using. And we did see that the impact also varies heavily across models of different complexities. Similarly, it is also certain that the impact will also vary across data sets. For example, if you use satellite imageries, which are very heavy images compared to the smaller real world images that we used, the impact will vary. And there the decoding would play a much more important role. And the impact can also vary across when you go into distributed training and you have different number of GPUs. And then also it depends on how you would configure the NVIDIA DALI library to use it with SageMaker in this scenario. So yeah, that's more or less what I had in mind to discuss. I see we are already at the top of the hour, but what I could do now is move on to the chat to look into some of the questions. I didn't have the chance to look into them.
Yes, thanks so much, Shayan. Really, really great talk and session and topic as well. There's a couple of questions. So yeah, if you could have a look at them. One was around the framework version. So PyTorch version, I think it was 1.81 that you used, right?
Yeah.
And Any other dependencies on a specific SageMaker version, debugger version, anything? So I think you had one slide in the beginning calling out all the dependencies, right?
Yeah, I see the chat now. Thanks, Antje, for already providing some of the links. That helps. Now, apart from that, I think the estimator version, yes, you can choose what estimator versions do you want to use on SageMaker. SageMaker comes with containers of different versions. And when it comes to the dependency, what you would do is in your source folder, you would have a requirement.txt file. And in the when you write the SageMaker estimator, you would only point to the source directory where you have the requirement.txt. And SageMaker will take care of downloading all the dependencies or all the external dependencies that are not there in that container or in that image for you. And in this case, with NVIDIA DALI, if you look into the GitHub repository, that's how we actually do it. Yeah. I'll quickly share with you the GitHub link of the repository. Yeah, I see a question. What are the cost performance trade-off between the CPUs versus GPUs? So in this case, every instance comes with certain number of CPUs and certain number of GPUs, right? So ideally, if you can pick instances with very large number of CPUs, then you can better distribute your augmentation load compared to the number of GPUs you have. But often you cannot pick that ratio and you still need to balance it better. So in that case, it's a trade-off between how many GPUs. Instead of using 4 GPUs, you can probably still use 1 GPU and train still in less amount of time. So I would say that's the trade-off that you would have. Can I change the Python version? Seems to come with 3.6. Yes, I do not have top of my head what are the exact versions available out there, but definitely when you use SageMaker Studio or SageMaker Notebooks, you can decide on picking up which version do you want to use. Would AWS SageMaker Debugger be a replacement for TensorBoard? Yeah, so you always have the flexibility. So debugger comes with one part of debugger is actually similar to what TensorBoard does, showing you the model specific parameters, and you can monitor the training loss or other custom metrics. But debugger also gives you the ability to look into system specific resources, system specific resource utilization, and also lets you have recommendation that probably your batch size is more, or you need to take care of your IO bottleneck. So it's a bit more, has a wider applicability than just TensorBoard. But at the same time, if you like using TensorBoard, you can also pip install TensorBoard in the requirement file and continue using TensorBoard and debugger. Yeah, is there something else I missed?
Yeah, we had an earlier question on have you played around with NVIDIA Insight systems? And question was whether SageMaker does support it.
So to be honest, I didn't have the chance to play around with this particular thing that you just mentioned. But in general, we have, so SageMaker also provides you with NVIDIA specific containers that you can pull from the NVIDIA cloud repository. So that's one direction that if you want to do something custom, you can always do that. And when it also comes to SageMaker training, you have the option to either use SageMaker built-in algorithms, but you can also bring your own script and use SageMaker container, which we are doing in this example. And if you do not have the container that you want on SageMaker at the moment, you can also bring in your own container and then push it to ECR and the container registry and let SageMaker use this custom container that you are building. So you have all the flexibilities that you want to use while SageMaker takes care of the infrastructure heavy lifting. Yeah.
All right.
I see a question between difference between Clarify and Debugger. So as SageMaker Debugger, as I already mentioned, it's more about tracking and visualizing your resource utilization, your training specific parameters, real time during your training. Clarify is more in the lines of when you want to understand which feature has more importance when you are training your models. when you want to understand more feature importance and dive deep into these kind of topics, that's when SageMaker Clarify comes into picture. So that's a stage before training that you would do. Yeah.
All right. I think those are most of the questions here. Also, I see there's a lot of questions still coming up. Aaron, I think you're still with us here in the session. So if people are interested in following up, should they reach out best via Twitter handles or LinkedIn? If you want to share maybe your LinkedIn's here for individuals who want to follow up on a more detailed conversation.
Sure, sounds like an idea. I'm gonna quickly drop my LinkedIn here.
So if people want to connect,
feel free to reach out.
That sounds good. Aaron, if you like, you want to share either Twitter or LinkedIn as well.
I will share those. Let me grab the link.
Yeah. We had a lot of good discussions today, so I want to give people the chance to connect and follow up if there's more interest. All right, so we do have the links in here. People, yeah, I know the copy paste from the chat doesn't always work. It's a Zoom security setting, but if you click on the actual link, you can open it locally, and that way you can grab it. So just click on those links, and that should take you to those sites, specifically LinkedIn sites. All right, and I think that is a wrap for today. Thanks so much, Aaron and Heiko and Cheyenne, for your great talks. A lot of great discussions today around NLP, and I'm super happy to also had a talk around bottlenecks in computer vision. I think that's also a very important one that we haven't focused a lot on in the past meetups. And with that, thanks everyone for joining and sticking around, and feel free to join us in next month's meetup. We'll update the lineup in a few days there. Thanks so much for joining, and have a great rest of your day.
Thank you. Have a good evening, everyone.
Thank you.
Thanks. Bye-bye.